So far, we have looked at problems where we're trying to find the work done by a force, as well as a few questions related to the potential energy stored in springs or elastic potential energy formula. And we have also looked at questions where we found the work done using the graphs. Now we switch to one of the core of work, energy, and power, which is called law of conservation of mechanical energy. If you've read the text, you will know that it says that in absence of any external force, the mechanical energy of the system remains conserved. What it means that if there are no external forces acting, right, the mechanical energy, which is simply a sum of kinetic energy and potential energies, remains constant, right? And usually, in case of gravity, which is also force, we consider the potential energy. Hence, we don't need to look for the external force, right? So basically, the sum of mechanical energy, right, is going to be same at all the point when there is no other external force, right? For example, in this question, calculate the minimum initial speed v of a ball must have in order to make it to the position B, right? So it says, if I throw the ball with a speed v over here, what is the value of v so that it can make it to the location B, okay? And then we have a certain question asked, right? So the key to solving this question is very simple. What we are going to do and argue is that the mechanical energy during this transition, right, during transition from location, let's call this O, to A to B, will always remain the same, okay, will always same. Why? Because there's no other external force acting on the system, right? If you look at this, there's no other force apart from gravity, and for gravity we are already taking that gravitational potential energy into account, so we don't have any other force acting on the system, right? So the key to solving this kind of question is that you choose a starting point which is O, so we write the mechanical energy at O will be always equal to mechanical energy at A, or will be also equal to mechanical energy at B, okay? And that's how we'll proceed, right? And that is going to give us all the answer, because the mechanical energy generally involves my half m v o square, right, which is the velocity at O, right, plus the potential energies at O, right? So let's calculate this. So here, when the ball is over here, we take the data for the potential energy here, right? So it is at zero height. So my potential energy will be zero. So all the energy which this ball has is simply half m into v square. Okay. So it has only kinetic energy over here. Now the question asks, what is the minimum initial speed v the ball must have in order to make it to the position B? Okay. So it doesn't matter, right? It has to go like this and then come back, right? Now, as you can see, for the ball to make it to B, it has to cross through A, right? Because the path is constrained, right? So once it crosses through A, basically then, it can very simply come here, right? So the minimum energy which is required will be to reach at point A, okay? So this is our initial mechanical energy, and at A, we are going to calculate all the energy and then going to make it equal to find the minimum value, right? So when we say minimum value, if the ball somehow just make it to the A with a very, very small velocity, right, it can simply roll and go down, right? So we'll assume that my V final at A is 0, right? We just need to reach over there and then we can come down to B pretty easily, right? So let's see what will be the mechanical energy at A. So mechanical energy will have two parts, the kinetic energy at A plus the potential energy at A. Fine. Kinetic energy, because saying in this limiting case, if the ball just reaches over there, right, so they're going to assume it to be 0, so my VA at A is going to be 0, so my half mVA square is also going to be 0, and the potential energy is the height mgh, right? So mg and the height is 4, so it's going to be mg into height is 4, okay? So that's 4 mg, okay? And by law of conservation of mechanical energy, the mechanical energy at a starting point must be equal to the mechanical energy at A, and we are going to simply make this equation equal to, the first one is half m into v square, right, where v is the velocity at location 0, starting point, and that is going to be equal to 4 mg. So m and m will cut, the 2 will go over there, and v will become 8 g, okay, and then under root, right? So this is the velocity which will be required for the ball to arrive at A, and then eventually it will go to B, right? We can put the value of G equal to 10, and then we can find the numerical value, right? So that's very easy. Now let's look at part B. Using the answer A, calculate the speed at B. Okay. Now, once we arrive here, right? So that's the velocity, right? That's the initial velocity, which is root under 8g, right? We have to throw the ball with that velocity, and then we have to find what is going to be my speed at location B, right? So in mechanical energy conservation problem, if the body is moving from one location to another via some path, we are only interested in the final outcome, right? So we are going to say, set up our equation like this. What is the energy at this location O? Okay, and then it goes like this, comes back to B, right? And we are going to say, what is my energy, mechanical energy as it is at B, and we are going to simply make it equal to mechanical energy at O, right? So let's find out what is going to be the mechanical energy at O, and that's going to be half into M into V square, right? Now we have found 8g under root, so the square when we do, it will become 8g. This is cut, and we are going to get 4mg, right? That is our initial mechanical energy at 0, right? And at B, right, it will have two components. First is the kinetic energy, so half into m into velocity at B square, and that is what we have to find out, right? What is the speed at B plus mg, at this time h, the height of location B, is 2 meters. Can you see that, right? We are directly applying that equation. So mg into 2. Okay, and that's our final, and these two are going to be equal, right? So mechanical energy at O going to be mechanical energy at B, and that's how we find this VB, the unknown, right? So we're going to make it equal to 4mg. It's going to be half m VB square plus 2mg. Oh, fantastic. So m will disappear. Now this is 4g minus 2g. That's going to be 2g equal to VB square divided by 2. Can you see that, right? So this is 4g, and this will go that side, minus 2g, and VB square by 2. So my VB is going to be 4g under root, right? And this 2 will come out to root g, right? You can find the value root 40, whatever that speed is, right? That's the numerical one, right? So that way we now know the speed at point B, right? Now it says if the initial speed, the value of V is 12 meters per second, calculate the speed A and B. Okay. Now this time, this 12 meters per second could be more than root AG, because that was a condition, right? That it can cross A, right? So now we are going to do and assume that we know the initial velocity, right? So here, when the object is starting, it has a kinetic energy which is half m v square. They have given the value of v, which is 12 meters per second, right? So this is going to be half m into 12 into 12. This is this 6. So we are going to end up 72. Okay. M. Fine. 72m. Fine. So that's our initial mechanical energy at O. And now we have to find the speed at location A. So we anchor over there. We write the total mechanical energy at A, right? Last time we assumed the velocity will be 0, right? This time it may not be 0, right? Because this time we might have thrown this with a higher velocity. So like that, into mg, and h for the height A is 4. This is 4. Okay, and these two quantities are going to be equal. So 72m is going to be m by 2 va square plus 4mg. mmm will eventually go off, so we are going to go 72, and this is like let's put the g value 10. So we'll get 72, 4 into 10, 40, and that will be va square by 2. So 72 minus 40, 32, and multiplied by 2, that will be va square. So that's going to be 64 va square, and va is going to be 8 meters per second. Okay, the square root of 64, right? Let's just quickly check the calculation again. So 4 into G 10, so that's 40, 72 minus 40, 32 into 2, 64. And then velocity at A is going to be 8 meters per second, right? We can now go and find the velocity at B again using the same argument, right? Our initial mechanical energy at O we have already calculated, right? Here 72 m. Okay, so this is 72 m. And now the object is going to go to B. So what is the mechanical energy at B? Mechanical energy at B is going to be half m into velocity at B square plus mg. At this time the h is 2, right? You remember the height is now 2, not 4. 2. Okay, so we are proceeding correctly. So this is 2 mg, so on and so forth, and these two will be equal. Okay, so again, in a very similar fashion, 72 m is going to be half m velocity at B square plus 2 mg. M cancel. Now we have the 72, and this is going to go into G, which is 20. So this time Vt square by 2 plus 20 is equal to 72. This will go on this side. We end up with 52. Okay, and then Vt square by 2. 52 into 2 is going to be 104, and Vb is going to be square root of 104, which is going to be roughly around 10, right? Roughly around 10 meter per second. Fine. So with that, basically you are able to solve the question. See, the key is to understand how the mechanical energy remains conserved. Just write the total mechanical energy at the starting point and the finish point and just make it equal to, and then look for what is unknown, like sometimes the velocity, sometimes the height, and with this you will be able to solve any question which you like, right? So law of conservation of mechanical energy, very, very important concept. We are going to do many more problems to clarify this. Please ensure you learn this uses of this and how to apply in a different situation.